Hello, AP Physics students. Today I'm going to record the lecture for Chapter 5, which is Circular Motion and Gravitational Force. I'm doing this split screen with the lecture on the right and the document camera on the left so we can easily switch between questions and example problems. Our first topic is circular motion and the kinematics of uniform circular motion. So uniform circular motion is motion in a circle, and the circle has a constant radius, and the motion has constant speed. The velocity, however, is not constant because we understand that velocity includes direction, and if an object is moving in a circle, the direction of its velocity is always changing. However, the instantaneous velocity is always tangent to the circle. So tangent to the circle, or we could say perpendicular to the radius of the circle. If we look at the change in velocity in the limit that time interval becomes infinitesimally small, we can derive the equation for the acceleration of the object. The derivation is beyond the scope of the course, but we can at least show the direction of that acceleration. So we know that change in velocity is ending velocity minus starting velocity. So here's ending velocity, v2. And to subtract starting velocity, we need to have starting velocity, but take the negative. So I'll take the negative of this vector by flipping its direction. Oh, it's not going to let me copy it. I'll just flip it like this. That should be about the same length. Yep. So v2 plus negative v1 gives us a delta V as such. This delta V points in toward the center of the circle. I can do this graphical analysis of V2 minus V1 for any pair of velocities anywhere in the circular path, and I always conclude that the acceleration is directed toward the center of the circle. So this acceleration is called centripetal. Centripetal means center-directed or radial acceleration, and it points towards the center of the circle. The magnitude of the acceleration is velocity squared divided by radius. Now we say velocity squared, but since we're squaring it, we lose the directional information about that particular velocity. It's the speed squared divided by radius, and then the direction is towards the center of the circle. For an object to be in uniform circular motion, then, to have that centripetal acceleration, there must be a net force acting on it. That net force must be in the centripetal direction. And since we know the acceleration for a uniformly circular moving object is v squared over r, we can use Newton's second law to say that the net force in the radial direction should be mass times acceleration. Net force should be mass times v squared divided by r. We're not defining a new force here. This is not a specific force called the centripetal force, but this is whatever force that's pointing in toward the center direction that causes the object to move in this circular path with acceleration v squared divided by r. We can kind of think about it in terms of a ball on a string, because the ball must be experiencing an inward force since the only thing it's touching is the string. Your hand, I should say the string is pulling on your hand and your hand is pulling on the string. The string is pulling inward on the ball. What happens when the string breaks or if you cut that string? It's common to think about centrifugal force. Centrifugal would be outward directed rather than inward directed. What happens is the natural tendency instead of the object to move in a straight line. So if the centripetal force stops, if the rope breaks, the ball does not fly outward. Instead, it stops following a circular path and it moves then in a straight line at constant speed according to Newton's first law. Here are some practice questions. So imagine a ping pong ball shot into a circular tube that is laying flat on a tabletop. What direction will the ping pong take? Which path will it follow? So we're thinking about the fact that this tube provides a centripetal force on the ping pong. The outer wall is pushing in on the ping pong. You should conclude that the ping pong will take path 2. That is the straight line path that is a continuation of the path it was taking before centripetal force ceased. A writer in A Barrel of Fun finds herself stuck with her back to the wall. I think this question only makes sense if you've ridden on one of these carnival rides. But you go in a circle in a tube and you sort of stick to the wall, the floor drops out from below you and you don't fall. So which diagram correctly shows the forces acting on this person? You can always pause this if you want to think about it before I show you the answer. So the correct answer is A. There is the pull of gravity straight down, and then there needs to be friction between her body and the wall pushing straight up. And then the wall itself is pushing in on her, in towards the center of the circle. The centripetal force needed to keep her in a circle is the normal force of the wall. And then as a result of the normal force, there's a force of friction pushing up on her. In a game of tetherball, the struck ball whirls around a pole on a rope. In what direction does the net force point on the ball? Well, we expect the ball to stay in its horizontal circle. So there's a component of tension that's up, and that component of tension up needs to be in balance with the weight straight down. Then there is a component of tension that's left over, and that component of tension points in toward the center of the circle. So the horizontal component of the tension force is the net force on the ball, and it's also the centripetal force on the ball. Now for a numerical example. So we'll switch to the document camera. Shoot, you can't see the question though if I do that. Let's try this. Whoops. Let's try making this a smaller screen. There. Okay, so a horizontal force of 310 newtons is exerted on a 2-kilogram ball as it rotates at arm's length uniformly in a horizontal circle. So the circle is horizontal, so I try to draw that like this rather than vertical, which would be like that. So it's a horizontal force, so pointing in towards the center of 310 newtons on a 2-kilogram ball, rotating at arm's length uniformly in a horizontal circle with radius 0.90 meters. Calculate the speed of the ball. So I'm thinking centripetal force is equal to mass times speed squared divided by radius. The centripetal force is that horizontal force, 310. The mass of the ball is 2 kilograms. Speed is what we want, and the radius is 0.9 meters. So 310 times 0.9 divided by 2 gives me 139.5. This is kilograms meters squared per second squared, or meters per second squared. We're dividing by kilograms, we're multiplying by meters, so we end up with meters squared per second squared. We take the square root. I'm not sure where the square root button is on my calculator. There it is. Of the answer, and we find that the velocity is plus or minus 11.8 meters per second. Plus or minus, it can be in either direction, and the direction doesn't really matter because we know that it's centripetal in nature. Next example. A bucket of mass 2 kilograms is whirled in a vertical circle of radius 1.2 meters. So we have this bucket, and it's on a string, and it goes around in a vertical circle. Okay, at the lowest point of its motion, the tension in the rope supporting the bucket is 25 newtons. The bucket has a mass of 2 kilograms. the radius of the string is 1.20 meters. We're supposed to find the speed of the bucket at this low point, and then how fast must the bucket move at the top of the circle so that the rope does not go slack. So first for A, how fast at the bottom. So similar to our previous problem, we're going to say that centripetal force is equal to mass times speed squared over radius. However, in this case, the centripetal force is the net force. The net force on that bucket, if I think about a free body diagram, is the difference between the tension in the string and the weight of the bucket. Tension, we're told, is 25 newtons. The weight of the bucket, mg, is 19.6 newtons. So the difference between those two is what's left over as my centripetal force. So my net centripetal force is 5.4 newtons. That's equal to 2 kilograms times speed squared divided by radius. So just as the previous example, we complete the calculation. I have to multiply by -1 in order to get rid of that false negative sign. So 3.24 for v squared. And so v is 1.8 meters per second. That's at the bottom of its path, and that's with the requirement that tension is 25 newtons and tension is bigger than the weight in order to have a net force in the centripetal direction. Now, how fast must the bucket go at the top so that the rope does not go slack? So now we zero in on the top of the path, and we think about this bucket upside down. All right, so here's the bucket, here's the rope. And again, I think about the forces acting on that bucket. So now at the top of its path, there's still weight pulling down, and tension is now pulling in the same direction as weight. If you're hanging onto the string down here, then you're exerting a force on that string in the downward direction, and this direction of tension has switched. So how fast must the bucket move at the top of the circle so that the rope does not go slack? So our condition that the rope does not go slack is to say that the tension never equals 0 or less. Right? If the rope goes slack, tension in the rope no longer exists. So I'm thinking about Newton's second law. Same as before, net force is mass times v squared over r. So we know the net force here is tension plus weight, mv squared over r. We know that the tension is unknown. We know the weight is, as it was before, 19.6 newtons. The mass is 2 kilograms. The v is what we're trying to find, and the radius is 1.2 meters. I'm just checking my numbers here, 1.2 meters. So the limit then, as the rope just goes slack, is that the tension in the rope just hits 0 newtons. So our minimum velocity, the velocity that you must exceed in order for the tension to not be 0, is found by setting tension equal to 0. At the speed where tension equals 0, the rope just goes slack, so you must have a speed larger than that. Now I solve for v. So 3.43 meters per second is the minimum speed to keep that rope from going slack. Now we'll go back to the lecture questions, or lecture slides. So to do that, I will make this bigger. Okay, on to slide 16. So when a car goes around a curve, there must be a net force towards the center of that curve, of which the curve is an arc of the circle, right? I mean, so we're just thinking about geometry. If the road is flat, the only force provided on the car then between the car and the road is friction. So there has to be friction between the tires and the car, and that friction points towards the center, or at least the net force of friction points towards the center of the circle. If the friction force is insufficient, the car will tend to move in a more nearly straight line. Again, the idea that the inertia of the car keeps it going in a straight line in the absence of the centripetal force needed to keep it in a circular path. And you can see those straight line paths in the skid marks of this racetrack, which is pretty cool. You see that those skid marks are straight lines, and then the sort of bulk of the tire mark on the track is a sort of fuzzy dark black line all around the circle, but occasionally cars skid out. So as long as the tires do not slip, friction is static. If tires do start to slip, the friction becomes kinetic, and that's bad in two ways. We know that the kinetic friction is always smaller than static friction, and the static friction force can point towards the center of the circle, but kinetic friction force always opposes the direction of actual motion. That opposition to direction of motion would then be pointing towards the back of the car, or opposite to the direction the car is going, that straight line path, and that makes it difficult to regain control of the car and regain the centripetal force that the car used to have with static friction. So now we have another computational question, and this one's about cars on roads. So again, I'll try to minimize this, maximize this. Oh, didn't work. Wait a minute, where did I go here? I just need to make this a little smaller. So we have a 1,200 kilogram car going around a 90 meter radius curve on a flat road. So flat road, meaning that we don't have to worry about the banked curve. And the coefficient of friction between the tires and the road is 0.65. So I can sort of imagine I'm like looking at the back of the car here. There's the car on the road. And if the car is about to turn to the left, then the static friction on the tires, or the net friction force, needs to point in towards the center of the circle. So this car is going into the page and turning towards the left. Friction needs to be in towards the center of that imaginary circle. So I'm saying that the net force on the car needs to be equal to mass times the speed squared over radius of the curve. That net force is provided by friction, so mu sub s times normal force, mv squared over r. But of course, because it's a flat curve in the vertical direction, we know that the normal force, or we expect that the normal force and the weight to be in balance, expecting the car to stay on the road. So mu sub s times normal force becomes mu sub s mg, mv squared over r. And we can actually see the answer to the second question, which is this result independent of the mass of the car? Yes, mass is on the mass times acceleration side of the equation. Mass is in the normal force part of the left side of the equation. So mass is not part of the answer. So again, we're searching for the velocity minimum speed, so v squared is equal to mu sub s times g times r, and then we might as well take the square root of both sides. So v is coefficient of friction, 0.65, times 9.8 meters per second squared, times the radius of 90 meters, and I got to take the square root of the whole pile. There's no units on mu sub s. It's just a pure number. So .9 meters per second. So it's like highway speeds, right? 50-ish miles per hour. I don't think there was another example question. Nope. So now we talk about what a civil engineer could do to make a curved road more safe. If you bank a curve, so incline the curve so that it tilts in towards the center of the circle, it can help keep cars from skidding. For every banked curve, there's one speed for which the entire centripetal force is supplied by the horizontal component of the normal force, and no friction is required. So there's a possible speed at a banked curve where friction doesn't play a role, and it's just the component of normal force due to the tilt that's pointing in towards the center of the circle. So this occurs when the normal force times sine of theta is equal to mv squared over r. So theta is the angle of incline. Mv squared over r is the mass times centripetal acceleration. I'm not sure if there's any banked curves around Salt Lake City. Maybe you can tell me, give me some feedback. Okay, on to some conceptual questions. So you're a passenger in a car and you're not wearing your seatbelt. Not a good choice. And the car makes a sharp left turn. From your perspective in the car, what do you feel is happening to you? So you make a sharp left turn towards the left. You feel thrown to the right. So you have a tendency to move in a straight line, and if you turn towards, or if the car body turns towards the left, your body is going to continue to move in a straight line, and you're going to encounter the door of the car on the right side. During that sharp left turn, you found yourself hitting the passenger door, as I just said. What is the correct description of what is actually happening? What is actually happening is that your inertia keeps you moving in a straight line until you hit the door, and the door then exerts a leftward force on you, and you then start turning left along with the car due to the centripetal now force, or the normal force of the door on your body. So now imagine, for those of you who are 16, on the holiday break, you drive your dad's car too fast around a curve. I hope you won't do this. And the car starts to skid. What's the correct description of this situation? Friction between the tires and the road is not strong enough to keep the car in a circle. So the force of friction between the tires and the road is too small. The force of friction is not equal to m times v squared over r, and so your car tends to go in a straight line instead of the curve. What if the circular motion of an object is not uniform? So if it's not uniform, that means that there is a component of acceleration that causes a change in magnitude of the velocity. So the velocity is still changing direction and the object still moves in a circular path, but in non-uniform circular motion, there's also acceleration along the direction of velocity, causing either a speed up or a slowdown as well as a turn. So imagine you're on a Ferris wheel moving in a vertical circle. When the Ferris wheel is at rest, a normal force is exerted by your seat, and that normal force is equal to your weight. How does the normal force change at the top of the Ferris wheel when you are in motion? You can answer it without physics just by thinking about how you feel, how your guts feel at the top of a Ferris wheel, if you've been on one. Normal force becomes smaller than mg. In order to remain in circular motion attached to that Ferris wheel, there must be a net force on you when you're at the top of the Ferris wheel that points in the downward direction. Your weight doesn't change, but the normal force can change. And so at the top of the Ferris wheel, the normal force needs to be smaller than mg so that you stay in a circular path. A skier, this is quite a picture here in this question. A skier goes over a small round hill with radius r. Since she's in circular motion, there has to be a centripetal force at the top of the hill. What is that centripetal force equal to? Think about the forces that are exerted on the skier and how they might be related in size. So similar to the story of the Ferris wheel, the centripetal force in total needs to point down in towards the center of the circle. So the weight of the skier needs to be larger than the support force of the snow at that point. So normal force is smaller and opposite in direction. Centripetal force is equal to weight minus normal force. You swing a ball at the end of a string in a vertical circle. Since the ball is in circular motion, there has to be a centripetal force. At the top of the ball's path, what is that centripetal force equal to? Hopefully now you're getting the hang of it. So now we have, instead of an upward normal force, we have a tension that's pulling in towards the center of the circle. So in this case, the centripetal force is tension down in towards the circle plus the weight of the ball. I'm going to stop the recording now so that we have two parts to this lecture just for ease of uploading the video.